Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
We made it.
We made it.
We made it live. It's been a long time.
Yes. Hello, everybody. Welcome to another episode of Ask Us Anything About Electrochemistry.
Yes.
Yeah, it's been pretty busy.
It's been like a month.
It feels like a month.
I forgot what this was like. I forgot about everything. I hope I did everything correctly. It's been a long time.
I think
fact,
you did.
It makes me realize I should check all this. It looks like the settings are correct, and I probably should have checked that like 12 minutes ago instead of right now. But hey, this is what happens. You get high degree of professionalism when it's been a while and I forgot all the things. It's funny how you get out of practice with these things. It's
yeah, absolutely.
Like we do this every week and it feels like a well-oiled machine, and then it's been a little while and just kind of, there's been vacation and work travel and other things, and it's, just got to get back into the swing of it.
Yes. Yeah.
So
well, welcome everybody, and I think we'll just start off with just answering some of the questions that have come in. Again, please type your questions into the chat, and we'll try to get to your question as soon as possible.
Yeah, we will. And the first question here is from Last Wish, who says that, is there any relevance to plot cyclic voltammetry for a primary aluminum air battery? So my thoughts about this are, generally speaking, no. Although it is possible there could be some, I don't know, relevance is the right word, but or just use in such a plot. So very broadly speaking, with batteries, cyclic voltammetry can be used, though it is not the main technique that is that useful, I suppose you'd say. Sometimes, for instance, when you are screening for different electrode materials, for example, you might say to yourself, okay, well, I want to test this material as an anode or as a cathode for whatever battery, whether it's primary or secondary battery. I have, in theory, determined it might intercalate, some material or be able to perform this reaction in this battery, right? That's sort of what battery research can entail, right? And so you might make a simple setup where you run some voltammetry, sweep the potential, usually very slowly, and see if you get some, like a peak, or at least any sort of response that is indicative of, a reaction of interest, right? And so from that perspective, whether it's in a full battery setup or it's in a half cell or something of that nature, in almost anything, you often do voltammetry, whether cyclic voltammetry or linear sweep. You'll sweep the voltage around and check for those kinds of electrochemical reactions and behavior to see. So from that perspective, the answer could be a very tentative yes. So sure, you could do voltammetry on your primary aluminum air battery. Why I think most accurately, perhaps, the answer is no, is for a couple of reasons. One is that cyclic voltammetry on a primary battery, these two things cannot really coexist. Cyclic voltammetry implies that you're sweeping in one direction and then the other direction, right? So if you think about it, if you're cycling the voltage from, let's say, high to low voltage, that's like going from fully charged to fully discharged state, or some measure of charge to some measure of discharge. Well, if it's a primary battery, it cannot be charged back up. That's definitional, right? It only gets discharged. It only goes in one direction. So you cannot cycle back. You should not increase the voltage back to your starting point. Hence, do a cycle or cyclic voltammetry. That isn't a good idea. If the battery could do that, it wouldn't be a primary battery. It would be a secondary or a rechargeable battery. So perhaps just a terminology clarification, you might be able to do linear sweep voltammetry, which is to say you can start at the charged state, sweep down to a discharge state, and look for behavior. So that is possible. But the other reason why perhaps it's not all that useful is simply because voltammetry is used sometimes as an exploratory technique to look for, as I said before, whether this material will work or not. But the charging and discharging of a battery is often done with a rate characteristic, which is how much current or power or something can I draw over a certain period of time. And so that requires you to set a current, which is usually a galvanostatic procedure. Voltammetry is a potentiostatic procedure. So the current that you will get is variant. It's changing. It's dynamic, right? To discharge a battery that way is not ideal. It doesn't give you as much information about its discharge characteristics. You would normally want to say, okay, I'm going to, instead of sweeping the voltage at some rate, I'm going to pull a milliamp from this battery or 10 amps, whatever the size of the battery is, and see how long it can deliver that kind of power. You can think about it as like a smoke alarm or something of that, or a video game controller might have a battery in it. It's a primary battery. Most of the time, you'll have AA, AAA, or coin cell, button cell. These exist in our, electronics or home appliances, for example, and it has to deliver a small amount of charge over a long period of time to allow the thing to work. That usually means relatively constant current delivery over a, again, long period of time. So that doesn't lend itself to a voltammetric technique. It lends itself to a galvanostatic or current controlled technique. So those are the two things why I guess, in summary, this is probably not the ideal kind of a test to perform. Again, you would not cycle the voltage in a primary battery because that would entail charging it back up, and it's primary, it cannot be charged up. And then secondly, is that to really study a primary battery, you're probably going to be looking at discharge characteristics at a relatively constant rate. And so most probably you're looking at a galvanostatic discharge kind of process to study the battery characteristics. But I wouldn't say it is impossible in some sense, because voltammetry can be used on irreversible process. Like, you don't have to have a reversible process to do voltammetry. It's just that the specifics of a primary battery means that you really ought not to try to charge it. You could actually have catastrophic effects. You could cause failure and fire and damage and things like that can happen when you try to charge up an irreversible primary battery. So I wouldn't recommend that.
All right. Moving forward, Altan says, hello, thank you for this Q&A session. Alton goes on to ask, I have a question. Do you know how continuous glucose with electrochemistry works, or EC works? I am confused on...
I assume that means electrochemistry, but I'm not sure.
I assume it does too. Mm-hmm. It's like this, the mechanism by which a continuous glucose monitor works. Mm-hmm. I am confused on how can it be continuous if the glucose binds to the enzyme irreversibly. And I'm by no means an expert on continuous glucose monitoring, but my take on it is, like, if you use glucose oxidase, for example, the glucose oxidase binds with the sugar, but it produces peroxide, and peroxide is actually the thing that we are electrochemically measuring in some of these sensors. So this is at least how we have a lab that's based on enzymatic detection of glucose and like beverages, fruit juices, things like that. And you use glucose oxidase, you measure the peroxide generated from the reaction, and on a platinum electrode, and maybe in a commercial one they use a different kind of material, but on that electrode you can very easily oxidize the peroxide, figure out how many electrons transferred from the current, and that will give you a measure of how much glucose is, in this case, in bloodstream. So I think based on this, the glucose and the enzyme itself actually is consumed. It is consumed. But the reading, maybe they have enough of this enzyme, they have such an abundance of this enzyme that when it interacts with the glucose, generates the peroxide, and then you do the electrochemistry reaction, um, the measurement of the glucose is not limited by how much of the enzyme you have. It's limited by how much of the glucose it is. And so by that way, you can determine that, hey, the concentration that I'm measuring of peroxide of glucose is actually accurate. But continuous glucose monitoring, it's not like indefinite. They have to like replace them or change them over a certain period of time. It's just way more convenient than somebody who has, is using just like kind of the finger prick method. Instead of pricking their fingers, 3-5 times a day, they just have a sensor, it's implanted, and they just replace it ever so often, like once a month. Much, much easier, much more convenient than pricking your fingers, every, you know, five plus times a day. So, and so that's one thing that's very, very helpful. But that's my understanding of how a continuous glucose sensor works. Um, anyway, I don't know if you have anything
I don't
else,
have a lot of
but
experience
yeah,
with glucose monitoring, but my answer is along those same lines. I mean,
I think
the
that's
fact that it's bound to the enzyme doesn't invalidate electrochemistry. Like electrons
yeah.
can still transfer, and
Mhm.
so that allows you to continuously monitor. I think perhaps it seems like you might just have some presumption that a molecule being bound in some way precludes it from um, uh, performing electrochemically, and
Mhm.
I don't know that that's true. I mean, the
Yeah.
molecule's still there. It can still enzymatically either it can be electrochemically reacted, or it enzymatically will produce peroxide, which can then be
Yeah.
detected. But yeah, I think all of that is how it works, I
Mhm.
suppose. But yeah, like just like you, I don't have any
Yeah.
personal research experience with like glucose monitors, other than just my general knowledge of electrochemistry, I suppose.
Yeah.
Sergey is joining us on LinkedIn. Uh, and he says, "Hi, thanks for the stream. For the ORR reaction, oxygen reduction reaction, is the traditional onset potential relevant, or is it better to give the potential at certain current density, for example, minus 0.1 millionth per centimeter squared?" And then he's a second question. But I think that it does tend to be more common in my observation. Um, these days, I feel like I see more people referring to it this way. The second thing that you said, a lot of people tend um, to prefer the reporting of, let's say, the potential at which I get like 10 milliamps per centimeter squared or point one, whatever the number is. I mean, the numbers are, I don't, it, I guess it depends on the catalyst perhaps, or the state of the art or whatever. But a lot of people are looking for that, like a specific current density. Um, and primarily because it's a little more comparable in the literature, for example, because it's normalized to surface area. There's open questions there, right? Is it the electrochemically active surface area? Is it geometric surface area? Are they the same? Are they not the same? There's a lot of follow-up questions. But in theory, if we assume we're normalizing by surface area, whether your catalyst is large or small, there's a normalized current, so that's applicable across different data sets, different labs. You can in theory say that that's a better metric to use, and then a certain amount of current density, as I said, and as you noted here, 0.1 or whatever, 10, whatever the number is. In theory, you're looking for the lowest over potential. So the oxygen reduction reaction occurs at 1.23 volts. So if we're saying, okay, well, it should dip down at 1.1, that's 100, 100, whatever, 20 millivolts over potential. And then this other person gets it at, 900. So that's a bigger over potential. That's bad. That's taking more energy to get the same current density, et cetera. So some of those kinds of reactions or interpretations, in my estimation, when you're talking about that metric, that's usually, again, based on, I might be wrong, and it might not be in all cases, but that is my assumption, is that when you're looking at that way. Now, to your second question, in a lot of cases, people aren't as concerned about the exact current density, because a lot of times, especially in an academic setting, you're actually doing more like proof of concept. You're just looking at the curves, you're trying to study it and get things like the number of electrons transferred, to look at the efficiency. Is it the 2 or 4 electron process? Is it producing water or peroxide? These kinds of things for the oxygen reduction reaction, which leads into your second question, where you said for the ORR process, which technique is more suitable for the determination of the electron number, Katecky-Levitch or direct calculation by RRDE? You're using an iron nitrogen carbon catalyst, I guess, of some sort. So, to be clear, I don't really know what you mean by in a differentiation between Katecky-Levitch or direct calculation by RRDE. I guess maybe you're referring to like a generate collect experiment or something of that nature. Yeah, maybe that's what you're talking about. That does make sense. So, for instance, a generate collect RRDE experiment is one way to sort of roughly obtain N, because if we're saying in an acidic environment, for instance, the oxygen reduction reaction can go through a 2-electron process that produces peroxide, which is detectable at a ring electrode, or a 4-electron process where water is produced, which is not detectable at the ring. Then we can basically get the portion of the ring current that is reacting with peroxide, and calculate what our N is, right? And if the ring current is there isn't any, it's 4, and then you could use a ratio of currents essentially and get it that way. I think a lot of people use that method. It's fine to use that method to get an estimation. You have to be a little careful, only for a variety of somewhat practical reasons. So you have to take into account the collection efficiency of your RRDE tip. I'm just mentioning these things. Hopefully you know these kinds of things, but still bears mentioning. You have to take into account the collection efficiency of your ring, because that you want to normalize your current based on the collection efficiency. That's a geometric property that basically limits how much the ring will see. It's usually somewhere between 25 and 35% based on the size of the ring and disc and things, and the gap between the two. And then the hydrodynamics, you want to check your collection efficiency, make sure it's accurate. Sometimes as you scan faster, if it changes, you might get cavitation in your cell. Like there's some inaccuracies with this method that can occur. And so it's not perfect, but it's reasonable, and it's reasonable in this reaction because we make the assumption, and again, this also could be somewhat faulty, but nevertheless, we make this assumption that there's just 2 possible reactions that are occurring for the oxygen reduction reaction, which are the 2 that I talked about, the 2-electron and the 4-electron pathway. And so we can directly correlate the current at the ring with just peroxide formed, do stoichiometry, figure out how many electrons were transferred in that, and then you can calculate your number of electrons transferred, and usually people get something like, well, it was 3.74, which means I had this percentage of the 2. You just do the math out. This is this percentage of the 4, this percentage of the 2. Okay, whatever. That is one way to do this. There's an error associated with that, obviously, just simply because the current picked up at the ring might not, you might be making an assumption that's not perfectly true. There could be some other reactions occurring that lead to the current at the ring or the disc. Background processes could be contributing somewhat to the currents you're getting, right? These are just some of the things that can lead to the quote unquote direct RRDE calculation being slightly more inaccurate, which leads, to the preference of doing the Katecky-Levitch method. I'll just kind of show some slides with that. I have some from a webinar. for what it's worth here. So the Katecki-Levitch, which actually is more of a Tafel analysis, but this is the Katecki-Levitch equation. More broadly, it's the 1 over the current is the sum of the inverse of the kinetic and mass transport limiting, diffusion limiting current that we get from the Levitch equation, which is here. And when we do a Katecki-Levitch analysis, we plot 1 over the current versus 1 over the square root of the rotation rate. And then we have all of this stuff as part of the slope, and we have the kinetic current as the intercept. From that, we get the kinetic current from a Katecki-Levitch plot. And the kinetic current can then be used with the Tafel equation to get the number of electrons transferred. So the Tafel slope, when you make a Tafel equation, which comes from the Katecki-Levitch, but it's not directly a Katecki-Levitch analysis, it's the Tafel analysis usually. And so what people sometimes do for this, you can think of it as a little more, I don't know, rigorous in some sense, because you're taking into account kinetics and mass transport of the real current that you get. So that sort of takes into account all of the things going on, so to speak. You might consider this a more accurate way to get kinetic information. It is certainly considered a pretty accurate way to get kinetic information, which directly leads into the use of the Tafel equation, getting you the Tafel slope, and therefore the number of electrons transferred, which is typically the thing that you're getting out of the Tafel slope. And so for your system, for instance, an ideal Tafel slope is 120. And so if that's divided by 4, you would get a Tafel slope of 30 millivolts per decade, for instance, and that indicates N of 4. I will be fair that the downsides of using that analysis, for instance, are that technically the Tafel equation and Katecki-Levitch, these are meant to be used. I'm not sure if I have these assumptions somewhere. I might not have them written out in these slides here. It's built-in assumptions of an irreversible process, 1 electron transfer, fast, usually pretty fast. These are some of the assumptions that are usually built into this kind of process. Well, already there's a bit of a contradiction because we're talking about 4 electrons transferred, and we're sort of assuming it's a 1 electron transfer. You get around that assumption by making the claim that 1 of the electrons transferred in the ORR is slow and the other 3 are fast. And so you sort of use it anyway. I'm just pointing these things out because I actually don't think per se to your question, Sergey, that there's necessarily one's better than the other. I think you would use both and maybe compare them, or at least use them in complementary way. You could talk about them and say, well, if one of them gives you 12 electrons and one of them gives you 2, something's wrong. Like check, but probably you'll be relatively close with both. Hopefully, if your experiments working out relatively well, and then it's just something to use as a point of discussion. You can perhaps even include one or the other or both. Discuss about the pros and cons of using each based on the assumptions I just kind of talked through. And this is the last thing I'll say, I guess, is that with ORR in particular and acidic media in particular as well, the good news is that we have such a massive corpus of literature on it, right? And everything that I just described is really part and parcel to that set of knowledge that we have of ORR, especially in acidic media, such that you have the ability and the benefit of using these multiple different methods, as opposed to maybe a lesser studied or lesser well-known, maybe electrochemical reaction where you might not be able to rely so much on a lot of other researchers' results or just easy methods of, the 4 and 2 electron pathway and all that kind of stuff. So I would not necessarily recommend you get rid of one method for the other. I would suggest using them both. You might get complementary information.
All right. The next question comes from Last Wish. Thank you for the clear explanations. How can someone get oxidation and reduction peak without doing cyclic voltammetry? So I think this is in regard to
I guess if he's doing he's still working with a battery. So
Yeah.
I
mean,
but you still want to get like,
I mean, by definition, a peak comes from voltammetry, where you get a kinetic and then current decay from a mass transport response. Like,
yeah, if you're doing another kind of voltammetry, like you
yeah.
can get some peaks, but it's not like you still have to do voltammetry though at the end of the day.
Right.
So, I mean, most people, and I guess I don't know if I would say most people, but like a lot of people will do cyclic voltammetry when they're studying the fundamentals of a particular chemical reaction. Once they know what that is and they decide to build a battery around it, there's no need to do any more cyclic voltammetry or determine what the peaks are. Like, oh, you now know what the redox potentials are for a specific system. You could build it into a battery, but you're not going to then take that battery and then try to do CV on it to determine where the redox peaks are. You already did that in a previous experiment. So that's kind of like where my head's at, when it comes to like getting an oxidation and reduction peak without doing CV.
The only thing I will add is that sometimes you do voltammetry on the battery when it's fully constructed, even though you know it works, right? Or you know you've done that. And the only reason for that is because the one thing that you often cannot capture as easily per se until you've constructed the battery is the SEI formation.
Correct.
And so sometimes the first scan you'll do with voltammetry really slowly, because you get this big, usually reduction peak, which is the SEI formation. So sometimes you do that. But even then, it's like a primary battery. It's not really like, you can't go back. So
you can't go back.
It almost feels like doing voltammetry on a primary battery is a way to waste a battery. Now, if you're going to learn something from it, that's okay.
Yeah.
But with a lithium ion or a sodium ion or a rechargeable battery, well, you can just charge it back up, no problem. Right? With a primary battery, it's like as soon as you sweep the voltage down and set it down, down to the bottom, well, it's over. Like, throw it away, get a new one. Like, what's the point?
Yeah.
So, unless you learned a lot, I guess that's But if you knew that it was redox peaks already, then all you did was confirm what you already knew, and then you wasted the battery.
Yeah.
Maybe I'm being cynical. Maybe there's more you can learn from it, but
I mean, maybe like last wish, if you want to comment a little bit more about like specifically what you're trying to get, like why do you like, if you know the material of your aluminum air battery, then you can do experiments separate from the battery for a CV if you want to get some peak information, but doing it on the battery itself, I'm trying to help us understand a little bit more about like what you're trying to measure, where you're trying to get, because even if you determine what the potentials are, it's like those are literature values probably. So you don't need to do that extra experiment. But let us know what you think, and we'll move on, try to get to some of these other questions as they come in. Looks like we have another question about batteries. Hi, Mary, thanks for the session again. Joining this one after a long time. Yes, it certainly has been a long time. I wanted to know, for a metal air coin cell battery, which is a primary battery, if I want to discharge the battery with constant 5 milliamp current, then in that case, which one should be my working electrode and which one should be my counter electrode?
the cathodes are working.
The cathode,
the cathode's the working, the anode is the counter.
Yep. And then you would just set it to 5 on your potentiostat and galvanostat.
Minus 5.
Okay. So you set it to -5 in that case.
Yeah.
And if you switch them and then set it to 5, then it would do that.
Yeah. The trick is with a battery, whether it's primary or secondary, the working electrode is invariably the cathode. The counter and reference electrode goes to the anode. And when you do that, you discover there's a positive voltage. So if you connect your potentiostat and you discover there's a negative voltage, switch to leads.
Yeah.
The correct polarity with a potentiostat or a battery cycler is that you should have a positive voltage, which typically occurs with the cathode on the working, anode on the counter and reference. Negative current corresponds to discharge. Positive current corresponds to charge. Discharge is sort
Okay.
of definitionally where the cathode is reducing and the anode is oxidizing.
Okay.
That's a discharge
That's a
process.
discharge process.
Um,
I never get these conventions right.
yeah. The reduction occurs at the cathode during discharge. So you have a negative current on the working electrode, hence a reduction at the cathode.
Mhm.
So that's the convention.
And that's the convention.
Yeah. Follow up if you needed a clarification of that. I can draw it if need be, but that's the convention that you should expect when you're setting up your battery. And then Tamogna has a second question. If I want to find out amount of chlorine and bromine ions mixture with silver nitrate using potentiometric titration, could you explain what is the basic electrochemistry principle behind it? Potentiometric. I haven't done potentiometric titration. I'm trying to think.
I mean,
is it just setting a potential and then what's the standard?
I think it's still a thing where like you add an amount of a species that reacts with the ion of in question, the analyte, so the chloride or the bromide, and then but that gives you an electrochemical signal. And then like you would do CV or something like that, and you would notice like, oh, as I keep adding more and more of this thing in, like the peaks like decrease or something until you've run out of that species, until it's binded to it.
So the first thing is that I think what's confusing to me is the electrochemistry part of this, because if you have silver nitrate is the only salt of silver that's soluble.
Yeah.
Right. Silver has a very low KSP. Silver, everything. Silver chloride, silver sulfate, whatever. Silver's always a solid, basically. Almost always. The only silver, the only anion with silver that will dissolve in water in any appreciable amount is silver nitrate. So what this means is that if you have chloride around, as soon as it's there, it just precipitates. You get AgCl that dumps out of solution. You see a silver wisp. I assume silver AgBr as well will do the same thing. I haven't tested silver bromide, but I assume it does the same thing. So I think what I'm confused about is even like where the electrochemistry plays a role, because I actually did this when I was in graduate school. It's called the chloride test. It's when you have like I made a transition metal oxide catalyst. The precursor material had chloride. It was like nickel chloride or whatever it was, right? And I was like rinsing it with water to try to get rid of the precursor materials. And that included whatever salts. One of the salts was chloride. And it's really critical to get rid of chloride. Chloride's bad for electrocatalysis. It binds to active sites, all this kind of stuff. And to test the precipitate for chloride, the way you do that is you make a small solution of silver nitrate and you add a drop of it. If you see silver, there's chloride. There's no this is all similar to what you're talking about, but there's no electrochemistry here, right? Or maybe there is, but there's no electrode. There's no potentiostat required. You just drop the solution. It's just chemistry, right? Ag locks up with Cl minus, if there's any, makes a silver, either drops out of solution or makes it gets cloudy. Like the solution gets kind of cloudy. And I actually don't know where electrochemistry is needed in this process or how it would even work. So I think I'm a bit at a loss of how to help in this regard. Do you have any other?
And I'm looking at some more
potentiometric
stuff.
titration.
Yeah. So it's like you're measuring the potential while you titrate something.
So maybe that's an additional thing you can do, is what I just described in some manner, where you either you have AgNO3 and you add chloride, or you have AgCl and you add, I don't know, something, and then but you're simultaneously measuring the potential.
Yeah.
I guess. So maybe you can explain why the potential would change. It's your favorite equation.
Favorite equation.
Why else would it change?
Yeah, why else would it change? I
just set you up. I mean, you gotta.
I know, you just set me up for this.
There you go.
But yeah, the basic kind of electrochemistry principle behind this is, hold on, I have to move this up front. The Nernst equation. So
there it is. It's been a month, but never lose the Nernst equation.
Never lose the Nernst equation. So the fundamental chemistry principle, if you will, is that the potential. So this is the Nernst equation. It just states that the potential of the electrode is equal to the standard potential of the redox reaction. And in this case, we just have this as the redox reaction. But in the case of chloride, and in fact, silver chloride, you'll have a different reaction that governs it, but there's a potential associated with it. And it's equal to minus RT over NF, the natural log of the activity of like your reduced and your oxidized species, any aqueous species that are in solution, sort of say. So all this means is that the potential that you measure will be directly related to the activity, but really the concentration of the chloride in your solution. So as you're adding, so the reaction for silver and chloride in particular is, let's see if I get this right. So you usually have, let's see, it's let's see, and we always want the ox on the bottom. So we usually, all right, let me get rid of these so that I remember it. But usually it's something like Ag plus. Here, I'm gonna write it because I don't want to add subscripts. I'll just use the whole review marking thing. And let's see. So it's something like silver Ag plus plus an electron. And then I think there's also, let's see, where is it? There's
AgCl plus an electron.
It's AgCl plus an electron.
I just looked it up to help. I wouldn't have gotten it if I didn't look it up either. AgCl plus an electron goes to Ag solid with this, and then plus Cl minus.
There we go. Yes,
that's
right.
Yeah.
Plus Cl minus. Charge is balanced.
That's it.
Chloride is the only thing here. So really, you end up having like natural log. It ends up being something like, the natural log of the chloride ion concentration. And maybe it's, plus or minus depending on how you write this reaction. But either way, you end up getting a case where the amount of chloride in solution changes the potential, and that's something that you're directly measuring. So you have the chloride in your solution. You keep adding something to change this amount, and then until you reach a certain level where this usually needs to be like 1 to 100 for you to get, say, when this moves by order of magnitude like 10, you end up getting like a 59 millivolt shift or something in the potential. So when you go to like 1 to 100 or 1 to 1,000, you then have like another 59, another 59, another 59 millivolts. But that is how you can then determine what the potential is. What the measured potential determines how much chloride's in your system. And then you have a similar reaction with bromine, and it would all be based around the standard potential for this reaction. And that would be the same case with silver bromide. So that's the fundamentals of the basic electrochemistry by why potentiometric titration works. Glad we figured that out, because I'm like, what is this titration technique?
We should keep that slide up for the next question.
Oh, really?
Barry's back. So he says 2 questions. The second question is related to what you said. So how does temperature affect the Nernst equation?
Yes.
And then the first part was why would his ferrocene FCFC plus broaden from 70 to 120 or more he's got 0.1 molar TBAPF6.
Yeah.
So why is the peak splitting getting too wide? And then how does temperature affect the Nernst equation?
Well, I'll answer the temperature affects the Nernst equation one very simply, just based on just bringing this back up, because that's like the
before you let it go.
Before I let it go. It's kind of hard to say. I just look at this and I say, when temperature here goes up and down, it'll affect the math involved when you plug all this stuff in. Yeah. That's and this will be true to a degree. If you go to super high boiling point temperatures or freezing point temperatures, it's like, well, then this starts to break down. But more or less, a 1 degree change will have a linear impact when multiplied by the log of the concentration to change the potential. So that's the gist, I would say, of how temperature affects the Nernst
I think there's
equation.
some rules of thumb as well, like
Mhm.
mathematically, isn't it? I don't know so much for temperature, but like for instance, 1 order of magnitude change in the
Mhm.
concentration is 60 millivolts,
Yeah.
right? If you do the math out, R times T, like room temperature, I know we're talking about,
Yeah.
to just take it for one temperature, for instance, over N times Faraday's constant. And then if you change from natural log to
Yeah,
log
to
base
log.
10,
Yeah.
you have a 1 over the log of E term that gets in there. That's like 2 point something. Like you could
Yeah.
just, these are just numbers. I'm not like showing them because it's hopefully
Yeah.
somewhat intuitive. But once you go to log 10, it's more intuitive. So when, for instance, in this expression that Alex has on screen right now, you can see, you get basically 59 or 60 millivolts effectively. So what that means is if you go from 0.1 molar chloride to 1 molar chloride, you will basically go down in potential by 60. It's inverse because you drew a plus, but really it's actually minus, right? Well, by definition, it depends on how you write your reaction, like you said, but by its default, when you're talking about the reduction reaction, the way it's written, you have it. It's the potential goes down when the concentration goes up. It's inverse. So, so 60 milliliters. So in a similar way, you can imagine for the same concentration, like it's linear. Like if you doubled the temperature, you're taking away double the amount of. No, I don't think it's 59. I have to think about it to do the math out a little bit. I guess it would depend on what the concentration was, but like the temperature change is going to just in a direct way affect that term. So if you want to know, I mean, just plug in the ideal gas constant, Faraday's constant, and the concentrations of whatever reaction of interest that you're working with, whether if it's ferrocene, put in the concentrations of the FC and the FC plus or whatever, do the math out and do it for a couple of temperatures and see, because you could see what it was. But it's going to be a similar kind of thing. As the temperature goes up, the potential should, in theory, drop because it's a minus sign and the temperature's in the numerator. So in theory, that's mathematically how it would relate, I guess. And then I guess the second part of his question.
Yeah, second part of his question.
The first part of his question.
Yeah, first part.
Why would a ferrocene peak split be wider? I mean, I guess could it be the catalyst is not great, or it could be something bound? Is it like surface bound species can cause that? Because ferrocene, like one of the answers to wider peak split is that the reaction is like not as reversible or something, but this is ferrocene. So in theory, it's like, well, we know the ferrocene reaction should be pretty reversible. Like it's, so it probably is accounted for by other factors.
At first glance, I'm thinking like solution resistance.
Oh, okay. Yeah, that too.
I think that's probably
0.1 molar TB. What's your solvent, I guess, is the other question. If you're in acetonitrile, that's probably the best case scenario, I guess. But if you're doing
even the position of the reference and the working electrode will affect your solution resistance a little bit.
Solution resistance.
You're doing stuff like that.
Uncompensated resistance can cause that. That's probably
because you're right. Like the ferrocene-ferrocenium redox couple has like super fast kinetics. It's like really, really good. So any peak splitting has to do, you could have some irreversible absorption. The electrode gets dirty. That's another thing that can also cause the peak splitting.
Yeah, but a lot of times it's uncompensated resistance.
Yeah.
Connections to your electrodes, the positioning of your electrodes, the electrolyte concentration. And if you have a solvent like DMSO or DMF or methylene chloride, for instance, they have just very high intrinsic uncompensated resistance. Even with high TBAPF6 concentrations, it's a pain. They can have a kilo ohm or something of resistance. It's crazy. And that can lead to those peak splittings.
Yeah.
So, okay. Let's see. Apurva has a few questions, I think, which is, she says, what to do if your Tafel value for best electrode is more when compared to the bad one for HER and OER? This happens probably because the best electrode has a higher current, more than 10 milliamp at the onset.
Right. What if your Tafel? When she says Tafel value,
I don't know what you mean by Tafel value.
Tafel.
Do you mean the Tafel slope, or do you mean trying to think here.
For best electrode is more
compared to
when
the bad one. Maybe you're saying that the Tafel slope is higher, which indicates fewer electrons transferred, and that's leading you to think it's bad. I mean, there's a lot to think through here. Obviously, without any other information, my go-to thing, crusade as a scientist here is to question all Tafel results.
yeah.
As I say once a week on this program.
Yeah, so she's purpose clarifying. Yes, I meant to say Tafel slope. Okay. So we are comparing Tafel slopes.
So Tafel slope being higher in theory means that the you're drawing the conclusion that the n, which is in the denominator of the Tafel slope, is lower, making the slope larger, meaning there's fewer electrons transferred, and that's bad. Let's just say, right?
Yeah.
I question broadly the method of making the Tafel slope, because one possibility is that you're producing Tafel plots and then therefore Tafel slopes is fraudulent, at least in some manner. Again, I feel like I'm on a soapbox every week saying this, but it's important. It's important to highlight this. The Tafel equation is a direct derivation of the Butler-Volmer equation, which is an equation that associates kinetic current with overpotential. I will repeat, kinetic current with overpotential. You cannot just take voltammetry data necessarily and convert it to a Tafel plot. Well, you can, but then it means nothing, and it's not really a Tafel plot. So I'm not trying to accuse anybody of anything. I'm just saying this happens a lot in the electrochemistry research community, is that someone does like an LSV or a CV or something or whatever. They just take any voltammetry data, they flip the axes, and they take the logarithm of the potential of the current, excuse me. And they say that this is a Tafel slope, and it's not. It means nothing. You must extract or ensure the current being plotted on a Tafel plot is kinetic current only. If you aren't doing that, your Tafel slope is meaningless, and the appearance of one being greater than the other is mere coincidence. And no further analysis should be attempted. In other words, if you're looking for why is one of them bigger than the other, the answer is because none of it matters. And you should make either a proper Tafel slope with real kinetic current, or you should abandon the process entirely. Yes, in some sense, ideally, the best electrode should have a lower Tafel slope. That would probably, in theory, mean that more electrons are being transferred. All other things being equal, it would mean that the symmetry factor and the temperature and all those other things are being accounted for properly. It's an irreversible reaction. If you're making your Tafel plot appropriately, then in theory the variable, so to speak, is the electrons transferred. And yes, under those conditions, the lower slope would be indicative of more electrons being transferred in theory. So yes, you have the right idea from a theoretical perspective, but I think even though considering the data points from the kinetic current region, I'm not getting it properly. So I think, hopefully you do recognize there might be some difficulty in getting information that you can associate as kinetic, purely kinetic, to be able to make these plots. Because the problem is, honestly, I mean this for scientific and academic integrity, is that you're going to make claims about the Tafel slope, the electrons transferred, and the kinetic and the mechanistic reality of your catalyst, and you'll be making that claim based on improper data, and that's not a good idea, right? It's just not. It's not good to make broad claims about how good or bad your materials are based on data that is not produced properly. You cannot really make Tafel plots without kinetic information. So I would encourage you to try a method that gets you at kinetic information more purely, something like a Tekulevich, or in some cases, very, very slow scan voltammetry over a very narrow range of potentials can, in some cases, be applicable. But otherwise, you have the right idea about what you're looking for with the Tafel slope. But I would not necessarily say that your conclusions about the Tafel slopes that you are so far getting are meaningful, frankly.
So Porter makes one last comment that I find very interesting, which is whenever the log J value becomes more than 1, slope value increases. So that's to say, because in a normal Tafel slope, like in the very start, things are curved. But then outwards, it's like a straight line. But then if you continue down on that straight line and then it curves again and the value changes, that leads me to think like, oh, you're now entering a region where there's like another reaction occurring or something else entirely different is occurring, right? Because according to Butler-Volmer, according to how a Tafel, plot looks, Tafel plots, they just look like they look like this, right? They just, if you just draw them and maybe
Depends on which axis.
I know it depends on which axis, but let's see. This is over potential eta, and then this is log J current density.
Mhm.
It starts off like this, kind of curved, but then it's like straight, right? That's generally what it's supposed to be. And if you're reaching a point when she said like when log J equals 1,
Mhm.
the slope gets, I guess, bigger. So like this, I never remember. Like, are we talking?
Yeah,
slope
which
this way?
direction? I don't
I never
know.
remember which direction.
I think about it the other way. So for me, I'm backwards for what you're drawing, but it's the same thing.
It's like, oh well, if the slope is like going like this,
Or just changing in any way.
and changing in any way, then something totally different is happening.
Yeah, that's a different reaction.
It's just a different reaction now that's occurring. May even be a totally different process. So so there's a part of me that's thinking like, because you're then you're using the Tafel, like any slope is a Tafel slope, but we use the Butler-Volmer equation to relate it to the number of electrons transferred and alpha and stuff like that. But it might just be, you might need to model it on something totally different when you have these changes, if you will, from the Tafel slope, because the Tafel slope shouldn't be changing outside of this region,
Right.
according to Butler-Volmer.
Or you could say, well, you should be limiting your measurement of the Tafel slope to the region of overpotentials.
Yeah.
Where it's flat, right?
Yeah.
If it's changing too much, it might be fine to have multiple different processes. And even in some sense, people will do these kinds of analyses. They'll show multiple different sloped regions at different potentials, different overpotentials. And that, I have questions about that, because it's like when you get to the second region, is the first one, there's still kinetic current from the first one. It's like now you're convoluting the current. It opens some questions about whether it's valid.
Yeah.
But you could, in theory, say, pick the flat sections, and those are a couple of Tafel slopes associated with those processes, and you can do that. But if it's changing, it just calls the whole thing into question. You need to kind of try to limit your range to where it's of kinetic interest of region of interest, so to speak, I guess. So nice to see you, Min. Thank you for the comment.
Thank you.
Appreciate
My drawings.
it. Yes.
Very funny.
It's good to have fans. Okay. Sorry.
Also, while we're scrolling through, Chris. Hey, Chris, I haven't seen you in a long time.
It's been a while, man. Good to see you,
man.
Well, I don't see you. You just see us. You just.
Well, we know where he is. He's at platinum.
He's at platinum. That's right.
Platinum.
Oh, man,
That's
that's a callback.
That's a callback right there.
Damn,
yeah.
that takes it back.
That takes
back.
back.
That's like episode 50 or something.
Yeah.
I don't know when that was. That was a while ago, but talk about inside jokes. Maybe only Chris gets that. Jeez, yeah. Okay. I think Sergey.
Yeah, we're going back to Sergey.
Yeah, we're trying to get through everything. We will get there, everybody. So sorry for those who are joining us in questions. We will try to, we see all your questions. We're getting to them. As we say, most weeks of this, electrochemistry just takes some time to talk through answers. So we'll get to them as quickly as we can, but we do try to give everybody, the best answers that we can. And sometimes it takes a few minutes. So
Yeah.
we'll get there. Sergey has another question. Thanks for the detailed answers. Yeah. Indeed, we make screening by RRDE, but the interesting samples at UAD Kentucky-Levitt. Yeah, that makes sense. Another question. Is the technique based on double layer capacitance measurement suitable for the ECSA calculation for the FENC catalysts, or only for carbon or monocompetent catalysts? There's a contradiction in literature since someone tells that this approach is not for iron carbon.
There is contradiction in the literature.
Yeah, that's not surprising.
Yeah, that's not surprising.
This is a great question. So my hunch is to say that you should be able to use it in theory. If someone is saying that it's not applicable, there's probably a good reason for that. And this is beyond my knowledge. For instance, there's probably some interaction associated with the iron and carbon, I suppose, that I don't, maybe the capacitance is non-uniform or something in that due to that interaction, I suppose. In general, to get ECSA, we have like the method on platinum that was very well known and documented that I've shown a number of times. 210 microcoulombs per centimeter squared is the, aggregate value for most crystal facets in platinum, and you can calculate that with a simple cyclic voltammogram. Most other materials are not as well documented, and so to get ECSA, we have to do other things. One of them you can do, for instance, as you said, is to get the capacitance and the surface area. If you have if you have a tabulated value of it of some kind, I'm trying to think. You could use the expression for capacitance involves that.
The area of the electrode, the dielectric.
Yeah. So if you know the dielectric, you're making some assumptions of the dielectric material and the distance.
Yeah.
There's some assumptions there. It's what's the distance of the.
Yeah.
So it's a way to get area.
It's a way to get area.
In theory, you should be able to do that. I guess my point to you is that in general, my answer is that in the absence of any other possibility, I don't know any other really good way for you to get it other than like a physical method, like doing BET analysis. You can get the specific surface area, like meters squared per gram, and then you know how many grams you have, and you can say I have this much. It's still geometric. You're making a leap to say it's the same as ECSA. Whether that's correct or not is, I don't know. Yeah, it's obviously somewhat incorrect because there's a backside to the material that's on the substrate, which isn't exposed. So it's not all, this is hard. This is a hard thing to do. I will just kind of broadly say. And all I can really say to you is that I don't have a specific knowledge of what the iron carbon interaction is that would preclude the use of that kind of analysis that I just described. I don't know. And I don't have an opinion on whether the literature contradictions are valid or not. But in the absence of any other method, my general advice is use it, because what else are you supposed to do? If you need to get at it, it's at least probably reasonable to use as an estimation. Even if you say there's a decent degree of uncertainty, let's just say, I don't know, or try to back it up with some physical method, like BET or otherwise, do an SEM and do a cross section, try to extrapolate surface area, get a particle size and assume spheres. You could do something where you try to, in a secondary or tertiary method, get an estimate of the surface area. It's reasonable to do this, because otherwise I don't even know physically how you would. And so you would just, the other option is just you don't get normalized values by surface area because you just don't know what it is. And then that's not maybe as applicable because you're saying, well, I got 5 milliamps. So what does that even mean? What's your surface area? I don't know. It doesn't help. Right. So I would say to heck with the contradiction, just go for it. That's my guess. But yeah, that's a good question. And the reality again is I wouldn't invalidate perhaps the claims of, well, this is inaccurate for these reasons because of some reaction between, or some interaction between iron and carbon. That may be the case. If you don't have any other options, I don't know what you're supposed to do. I'll be honest. So I would say, even from that perspective, it's not necessarily off base to say, all things, notwithstanding, we're still using this method.
All right. So trying to move on. Ahmad has a question. Can the CV be negative?
Does he mean like it's not, like it's very depressing? The CV is like giving you bad news.
If that's the case, that is true.
It's like you're trying to get a CV and the CV is like, no, you're ugly, and you're a bad researcher. What the heck? CV?
Negative. The CVs can be negative. You usually need to have a talk. Usually sometimes you have to bring HR in.
Yeah,
you gotta talk to your.
You just got to be more positive, CV.
Yeah, to be very positive. And you know what? Nowadays, if the CV is negative, you can just like flip the axes, and then
that's right. Just change your convention.
Change the convention.
All of a sudden, he's positive.
No, so it's all positive.
Amazing.
So, but yeah, that's to say that the axes, the current, the potential axis can be negative in a CV. And also keep in mind that there are conventions for plotting cyclic voltammograms. I'll actually, gosh, this is always something that
find the right file.
Find a file where I actually talked about this. Hold on, I think it was. Hold on, gonna go through this. Here we go. So let me just share my screen quickly. So this here is the two plotting conventions for voltammograms. There is the US convention and then the IUPAC convention. IUPAC stands for International Union of Pure and Applied Chemistry or Chemicals. I always have to try to remember what IUPAC stands for.
I never remember it.
The US convention has IUPAC convention is the one that makes sense from a mathematical perspective. If you think of this as like a grid, positive numbers are to the right, like a number grid. Negative numbers are to the left. Positive current refers to an oxidation. Negative current refers to a reduction. And reduction is adding gaining electrons. So electrons are negative. So all of this makes a lot of sense. The U.S. convention flips it. I think this was at one point described as if you do a C2 operation, like a geometry operation, like kind of like rotating it like on like 180 degrees. That's what the US convention is. So negative potentials are to the right, positive potentials are to the left. Positive current refers to a reduction and negative current refers to an oxidation. So these are the two conventions for plotting voltammograms. So just keep that in mind when you say, can CVs be negative? There are different plotting conventions. So just keep that in mind with regard to the units. Don't need to harp on that for too long. All right. Next question from Babu. He's asking, how can I set up HER and OER simultaneously in a 3-electrode system? If I'm running LSV, what could be right parameters? Well, in a 3-electrode system, you have a working and a counter electrode, and almost more often, if you're in aqueous conditions, let's say you have a platinum counter electrode, and then let's say you also have a platinum working electrode. When you're applying a negative potential to the platinum working electrode to get the HER reaction to occur, then an OER reaction will occur simultaneously on the platinum counter electrode. and vice versa. So when you're doing an LSV experiment where you're pushing the electrode to one extreme to do like the OER reaction or the HER reaction, the opposite reaction will need to occur on the counter electrode. So that's kind of how I'm thinking about this question. How exactly is it set up? Now, if you're talking about HER and OER on just the working electrode, then you would need to, they can't happen at the same time because they're opposites basically. So
It's not physically possible.
so you I think that's very hard to do. You know, I think I remember
that's not possible.
So
you can't both be at 4. You can't both be at 1.4 and minus 0.4 volts at the same time.
Yeah.
Just making up numbers. But basically, the HER's standard potential is 0.
Yeah.
Volts, right? The OER standard potential is 1.23. By definition, a reduction reaction occurs when the potential is pushed to a negative potential of its standard. An oxidation reaction occurs when its potential is pushed positive of the standard, which means that I have hydrogen evolution over here in the negative, oxygen evolution at the positive here. The oxygen evolution will happen positive of that. The hydrogen evolution will happen negative of that. All of this stuff in between isn't doing either of them. Okay, so to have them happen at the same time is physically impossible. You can't both be here and here at the same time. It isn't possible. But to Alex's point, when one electrode is over here, the other one is over here. So to do them simultaneously, it's through the mechanism of the working in the counter electrode. One of them is doing one, the other is doing the other. The problem is that you're only measuring one. You're really only measuring the working electrode. So while the working electrode is doing the OER, the counter electrode is probably doing the HER, but you're not really measuring it at all. You're not getting much information about that. The potentiostat is designed and the setup is designed in such a way to give you information about the working electrode pretty much exclusively. The only way to get information about both is to use a 2-electrode setup. You would have to get rid of the reference electrode and do a 2-electrode setup. This is effectively what's called an electrolyzer. When you would be doing something like that, you would have 2 electrodes. You're splitting water into oxygen and hydrogen, one at one electrode, the other at the other. And this is typically what's called an electrolyzer. It's a special device that performs that kind of reaction.
Okay. Yeah. All right. Yeah. Well,
so,
let's
follow up if you have any additional questions. But that's the answer there for you. So, okay.
All right.
So Apoorva.
Yeah.
So she says, can you show how gas purging can be done before an RRDE experiment in a Pine setup? If you have any image or video. I don't know if we have any images of it, like the bubbling specifically. Let me just.
Yeah, we can always put the.
Let me see. I might be able to. I think there's some images here. Let me take a look.
Just the dual port gas sparger.
I was even going to be more simple than that. Just the low volume cell. There's these.
Oh, okay.
So I'll show you in a couple ways, and I'll try to draw a few things, I guess, if it's helpful. Tab this. So, for example, this is one version of our cell. This is a low volume cell, RRDE cell. You can see, for instance, in this kind of cell, we have a gas. There's a number of ways you can do this, but one of the ways is there's a tube, that sometimes just sits into the cell. So like Tygon or rubber tubing here, and honestly, it's pretty simple. The way that this is done practically, let me draw a little bit for you. One of a couple of ways. So if I have my cell, I'll just draw a slightly bigger cell here, right? One of the ways is that we have a dual port gas piece,
yeah,
which I could have pulled up a picture of, but I'm instead of doing this. Right. So, and the way that that works is that it fits into the cell, and there's a top port and there's a bottom port. Okay. The top port usually is connected with a frit. Okay. And so what we would do is we would have gas in. Do I have this right? It's not backwards, right? I think that's correct.
Yeah,
The top
yeah,
one goes
that's
to the
correct.
okay, yeah, just making sure I had it right. So the top port of
Well,
this.
gassing goes to both of them, actually.
No, I know, but the headspace is in the bottom one. I
Oh,
believe,
yeah.
right.
Yes.
So you'd connect your gas to the top port, and this is for about 45 to 60 minutes before your experiment begins, and you would have gas flowing in, and it's going to bubble. You get a nice bubbling rate into your solution. It'll fizz up, it'll bubble. Sometimes you'll get a bubble kind of forming like at some relative. Don't bubble so fast that it's like spraying everywhere. You don't want to get acid onto the counter and stuff, but you want to bubble it enough that it saturates the solution either with oxygen or gets rid of oxygen by bubbling nitrogen or argon or something, whatever gas you're doing. And so usually you'll do that for, again, 45 to 60 minutes before you start your test. So your solution is here. And then when you start your experiment, you take the gas out of this port and you put it into this port. This is the one that goes to the headspace. So this puts the gas just into the headspace. And so what it does is it blankets the top of the solution with gas. And so that prevents any inflow of like oxygen or whatever from the environment from getting in, because you have a net outflux of gas because you're purging it in the headspace. But you don't want to disturb the solution because that would mess up the RDE or RRDE experiment. To accomplish this without the dual import, glass piece that I just showed you, it's as simple as here's my, even just a beaker, any system, whether it's a pine one, a fancy one, or it's just a beaker with some, solution in it, whatever your cell is. If you have a tube, you start by putting the tube somewhere in the water, right? And you have gas in, and so you'll bubble gas for a little while, 45 to 60 minutes. And then when you start your experiment, you're going to just lift the tube. And usually, I would do this when I was in graduate school because it was just very simple. In some cases, just let the tube rest. Now, again, if there's a port, if there's a fancier setup, that's fine. But just lift the tube to be in the headspace. And so it's flowing gas just in the headspace while you're running your experiment. Now, I'm not drawing the electrodes. The electrodes you assume are in there too. But that's just roughly how you do this. And again, 45 to 60 minutes is roughly enough time to guarantee that it's well saturated. That's practically how you do it. So please follow up if you need any other comments on that. It's a relatively simple process, and you just want to make sure, generally speaking, that you're not bubbling on the working electrode or the reference electrode or a Lugin capillary or things like that, because bubbles can get in the way, block electrodes and things like that. So make sure you don't get bubbles in the way.
Okay, so next question is from Last Wish. Kind of continuing this conversation about primary batteries, but he wants to suggest electrochemical characterization techniques for primary batteries.
Galvanostatic discharge is the main one. It's the primary one he'll do.
Get it, Tish?
Yeah. No. What if you're characterizing the primary battery, you're looking at how well does it deliver current for its lifetime, and so you have to just discharge it and see how it does. So what the main thing is to pick a current based on its capacity, based on whatever characteristics that of the battery, and apply that current and look at the discharge curve and see how long its voltage remains before it goes to zero or close to zero or something, and it's fully discharged. You can also do impedance. The impedance measurement necessarily wiggles the, usually you do galvanostatically, so you'll apply a current perturbation around a set point. That does in a very small way, charge it, discharge it, charge, because you're wiggling the current and or potential around a set point. And so some of the time it is technically charging, right? I just said don't charge your battery. If it's a primary battery, it's dangerous. You can usually do impedance because it's very, very fast. And the amount that it's going up and down is very minor and small, so you're not likely to damage it. It's relatively non-invasive. If your amplitude is too large, you could damage it. So start with a low amplitude and work your way up to get your data. But you can do impedance on primary batteries at various states. You could, for example, do it at the fresh battery, see what its impedance characteristics look like, discharge it for a while, do impedance again, discharge it for a while, do impedance again, things like that. That's probably the most common methods that you would use, I would say, to interrogate a primary battery, because you're limited certainly by your ability to test it further as you would with a rechargeable battery. You can't recharge it back up. So,
okay. All right. So moving on. Anticool. I think did I said that right? Probably not. Can you explain the CV in terms of current versus time plot? I couldn't find any duck-shaped plot, so I chose current versus time plot. It shows abrupt fall of current initially and then levels off. So I just pulled this up. So when you're doing like cyclic voltammetry and you get this kind of duck shape here, this is so this is your CV as you normally have it. And it gives you a duck shape. This is the applied potential that we applied versus time. And this is the current response as a function of time. So, and literally, we just kind of superimpose these two guys on the same plot, and that's how we get this duck. And so, yes, as you're initially scanning, that's like, this section here corresponds to this section over here. And then we get this drop in the current, in this case, due to reduction. This is a reduction reaction in this case. So we get a drop in the current due to the reduction, and then it starts to level off. This is as we would normally have. This is like a mass transport diffusion controlled process. So that's that guy here. At some point, we flip the potential. That's here. But the current is still kind of going the same direction. Like if you were to just extend this out, it's just going the same direction. But that's what we see here. The current is still just decaying as we're moving, but we flip it when we're doing kind of like the potential curve. We're still measuring the same current. It's still decaying, basically, even at this step. And then it eventually reaches this point of potential where we're then oxidizing the reduced species back. And then we see this increase in current versus time, and then followed by its normal decay versus potential. So again, you have this decay versus potential. So a unfolded duck in this case looks like this. This current versus time is just an unfolded, quote, unfolded duck. If I were to move, flip this guy around, I would or if I flip this section around, I would get this picture. So that's what the current versus time plot looks like for a cyclic voltammogram, and it contains the same kind of information. Oxidation and reduction reactions occurring associated with these peaks. So that's the basic explanation. If you want more about like the quote leveling off, that's just a mass transport related issue for molecules diffusing away from the surface. So I hope that answers your question. That is the explanation of a CV in terms of current versus time.
Yep.
Yeah. So yeah, let us know if you need any further clarification on that.
Barry clarified about the peak splitting with ferrocene. He sees new peaks when adding ferrocene after the initial substrate. CV scan solvents are in dichloromethane.
Very resistive.
Yeah, so it's probably IR drop.
Yeah.
Dichloromethane has it's tough, man.
Yeah.
You're never gonna get low IR drop with the only non-aqueous solvent that I know of that is close to water is acetonitrile. It's comparable-ish. It's still a little high, but yeah, otherwise you just deal with that. The solvent, it's just intrinsic, so it's tough.
Yeah.
Let's see. CZ says, I'm doing electrode performance testing in a half cell 3 electrode setup for electrolysis, anion exchange membrane using nickel felt as a working electrode. What would be the main electrochemical tests to do? Electrode performance test of a half cell with a nickel felt.
A half 3 electrode setup.
Electrolysis, anion exchange membrane. So you're testing the anode of an anion exchange membrane, like electrolyzer, half cell 3 electrode setup. Nickel felt. So, I mean, the first things to do are voltammetry to make sure you're getting the reaction of interest, for instance. I assume this is alkaline. Nickel is typically an alkaline electrocatalyst, especially if it's anion exchange. Do some voltammetry. It might be messy on a felt because the like if you're using like a disc electrode, the flow patterns are nice and uniform, I guess, because it's like a planar geometry. With a felt, it's kind of all over the place, like channels, it's porous, it's you have a high surface area, so you might get a messy, maybe it looks okay, but you might get a messy sort of looking CV if the diffusion is kind of all over the place, it's in pores, it's also outside the structure, you might get a bit it might look different, I suppose, but you should, in theory, see some activity at a whatever positive potential you're trying to do, whatever reaction of interest. So that's the first thing. The second is just potentiometry, amperometry, excuse me, because probably in theory you're looking for like what the current that you can achieve from the material, based on its surface area. Hopefully maybe its surface area, or its porosity or whatever. If it's a felt, right, you probably have some way to kind of know how much surface area you have. You might want to do something like, once you identify, okay, well, there's whatever oxidation reaction at 0.7 volts occurs or something. So pick a potential, applied potential, and figure out how much current you can get out of it. Maybe if you're producing a product, like a gas product, you might connect a GC or an MS to your system, to the headspace, to the gas, to monitor for the production. Like if this part of your electrolyzer or your system is supposed to make whatever gas or whatever product of interest, you might want to detect for the presence of that product being made, whether it's a gas or a liquid or something. That's one of the things that you might do. And so that it is not an electrochemical test, but it's in conjunction with an electrochemical test. So you'll hold the potential for a while, for example, that's a positive potential above the oxidation potential of what you're trying to do. That should, in theory, produce a stream of your product, and then you would connect it to some analysis instrument like a gas chromatograph or a mass spectrometer, and try to verify, or you collect some of the electrolyte and send it through an NMR later, and an NMR can be a means to detect the presence of some species. So these are just all sort of things that you might consider doing with your test. Those are, I guess that's all I can kind of think of in a very non-specific way. I guess, I maybe you have to know more about the specific system you're testing, but that's what I can kind of think of off the bat, I suppose.
There's a comment from Morgan who says basically that we showed up in in the YouTube search for fossilized artificial intelligence visualizing a forgotten machine.
What does that
And
mean?
I have no idea what it means, but we apparently showed up, so he decided to join the stream for a bit.
Does that mean that we are okay? Are we artificially intelligent? Like we're not intelligent, like we're fake intelligent, right? It's artificial.
Could be fake
Or
intelligence.
are we so old that we're fossilized? Because that's what I think this means, is
I
that
think
we're
that's what it means.
YouTube just thinks that we're so old that we're already fossils. It's not necessarily wrong. I'm just saying I'm very old.
Not wrong.
Yeah,
Not wrong.
it's true.
Well, thanks for subscribing, Morgan. We
Yeah, it's
appreciate that.
interesting search.
Interesting search.
Yeah, that's very bizarre. But anyway,
Let's see. So TT, I think is next. I mean, of course, we can always acknowledge that, Chris.
he
just
had the
his
platinum last week.
Platinum.
Platinum.
And let's see. Okay, so TT is saying hi. I don't know if you remember me or not, but I was in your last live stream. I was a complete mess in the electrochemistry and was lost as hell. Your words were indeed supportive and truly helped. Compared to last time, I'm happy to tell you that I'm improving somehow. At least the things I don't get are now narrower, and I can ask the correct questions. So thanks a lot. Well, hey, we're happy. We're happy to hear that.
I think we talked your question like at the end for like 20 minutes about just don't give up and ask.
Oh yeah.
It was like I don't know where to start. You just had so many sort of fundamental questions. I think
that
it was like a therapy session.
It was was the last one we did.
Yeah, I do remember this. I'm glad. I'm really glad to hear that. Keep at it. The only follow up I'll say, this is true of academics as well as athletic endeavors. I can tell you for sure in both of these arenas, you will go through periods where, for instance, I'm not trying to be discouraging. I hope this comes across as encouraging. It's going to sound discouraging, but I promise that's not my intention. Is that you were in a very sort of dark, negative place. You're feeling badly. I don't know what to do. I don't know what to ask. And then you're getting better. You're understanding. Your lack of understanding is narrowing. You're figuring out what the questions to ask, and you're feeling more positive about yourself, and you're gaining knowledge. Life is cyclical, and confusing times will come again. Remember this feeling is my advice to you, because again, this happens with you're working on an athletic endeavor. You're like terrible at a thing, right? A sport, a technique, whatever, right? Or learning something. And then you like start to figure stuff out and you feeling like, I got this. I know what I'm doing. Something is going to knock you on your butt at some point. I get like it's going to happen. And the proclivity, as humans, this is like psychologically true. Negativity hits harder than positivity hits positive. You know what I mean? Like negative hits badly in a worse way, generally speaking, than positivity like boosts us. For example, people are more upset when they lose $5 than happy when they gain 20 or something like that.
Yeah.
So the tendency will be the next time you hit a roadblock of some kind to be like, oh, I guess I'm terrible. I don't, whatever. And it's like, my encouragement to you is remember this journey, this start, right? Like you were down, you will get out of it. Every roadblock is just an opportunity for you to climb over and get to the next point. So don't let the next time you feel discouraged knock you on your butt forever. Like you will get through that too. You got to keep going. You know what I mean? I don't know if that makes sense. That's just kind of my thought. Cause I've had those moments where I feel like in athletics or even in my career, I'm like, I got that. I know everything. And then all of a sudden I'm like, I'm stupid. I don't know anything. I have to like fight the urge to be like so down and like, and you forget all of the like positives that you worked up to that point in the face of something that happened. It happens. I know that this happens. So that's my encouragement to you. And that sounded maybe negative, but that's hopefully encouragement. I'm trying to be encouraging.
No, I think you are encouraging. I just can I don't know. All I can think about is just like, just sounds a little bit like a movie villain or something, or just like, I want you to remember this feeling. I just want you to remember how well I beat you.
I
I
was
didn't-
born
yeah,
in the darkness.
I was born this way.
You merely.
No, adopted.
What is that?
You merely adopted
You
the
merely-
darkness.
I was
Yeah.
born in the
Yeah.
darkness.
Yeah. I don't know. Just like, I want you to remember
Remember.
this, TT. Remember this moment. I like.
Yeah, it's like,
Like,
very,
whoa.
it's very ominous. Like,
It's very-
whoa,
it's
I'm
like,
not
whoa,
trying to get
man.
weird here. Like, trying to get scary. I'm just trying to be real. Like, you're,
But
yeah.
it is good. It's good to remember, like, either bad times or good times.
I do this to myself all the time. I play
Yeah.
basketball a lot, and like I have weeks where I'm just nailing
Mhm.
everything, and then I have weeks where like I feel like, why did I even come today? Like I missed every shot. I didn't even move on defense. I feel like, why am I should give up. I should, and it's like, no, it's fine. Like
Yeah.
the best NBA players
Yes.
go 0 for 12 or something, and then but they're in the NBA. Like,
Yeah.
you can't,
Yeah, that's right.
you can't let that knock you down forever. Like,
Mhm.
fine, wallow in your own misery for a couple hours. Everybody deserves to feel bad for a little bit. Whatever. Misery loves company. Fine, but pick yourself up. You're gonna be fine. So there you go. That's my villain
Your
speech for
villain
you for the
speech.
day. There you
I
go.
want you to remember this,
I want
TT.
you to
I
remember
want you to
this.
remember this moment. Before we get to TT's actual question, though, we did get a question from Sandeep before. But I think we can get to this relatively quickly. Sandeep wants to know, what is the meaning of in situ, and explain situ. Can you explain like a proper, what does it mean? Examples. So in situ, it's funny because, yeah, when I was like learning chemistry and science and stuff, I'd hear about in situ and ex situ experiments, and I'm like, what is this? What is this phrase? Like,
It's
what does
Latin,
this mean?
right? It's Latin.
Yeah, I think it's Latin.
Yeah.
But basically, when someone refers to something being in situ, it just means it's making a measurement while the process is occurring. This is also to say there's another one, but I'll get to that later. So, for example, in situ, let's say you're synthesizing a molecule and you're monitoring the synthesis process by, say, okay, you have this thing going in a reaction. I take an aliquot of the thing out, I move it to an NMR, I take an NMR, and I get some NMR peaks. And then, all right, that's the thing. And then I go back, and then at another time later during the reaction, I take out an aliquot, I move to the NMR, and then I make another measurement. I get a different set of NMR peaks. And I keep repeating that process. That would be ex situ, the technique that's being used. I have to kind of separate the technique, the reaction vessel or the process that's occurring from the technique that is measuring it. If that same reaction were to be, quote, in situ, it means I would be doing the reaction basically in the NMR tube, and I wouldn't have to like move it in and out. Like, while the process is happening, I don't have to take an aliquot out. It's already in the NMR tube, in the NMR, and I'm just collecting NMR data. So in electrochemistry, for example, UV-vis spectroscopy, UV-vis spectroelectrochemistry is an in situ process where you apply the potential, you generate some kind of redox species, and then while you're generating it, you hit it with photons of light and measure the UV-vis spectra. This is in contrast to like electrochemically generating something, taking it out, moving it to a UV-vis, and then putting it in a cuvette and then measuring it. So that is in situ. So people want to measure things in situ. It tends to, it tends to be easier to do. You get more information. Things are not kind of lost in the translation from moving to and from your reaction to the instrument of analysis. There's another term. I know you didn't ask this. There's another term called operando. So you might also see that term thrown around as well. An operando just means if you're doing something on a more industrial scale, like catalysis, for example, you're doing like a big catalytic reaction. Operando means while the thing is in operation to produce a real product, you're able to study it or monitor it. That's really what it comes down to. And you'll have to like remove part of the reaction, mid reaction, sort of say. You're just measuring it on the fly. So those types of things, you build analytical instruments into the very reactor itself that the thing is happening on. So that would be operando. But that's what in situ means when people say they're doing an in situ experiment. Okay. Oh, in situ. Here we go. In place. In situ just means in place.
Yep.
Thanks, Chris.
In place, or what does it say? On site.
On site.
Yes.
Hopefully that is helpful.
Well, look at Chris, Mr. Latin expert.
Mr. Latin expert.
Way to brag on everybody,
La
Chris.
di da. All right. CD has a couple questions he wanted to ask. He says, I want to ask if I'm interpreting CVs and GCDs, galvanoscopic charge discharge, what points to look for to discuss for a pseudocapacitor to relate its behavior and how to signify these points? He has that one first. And he has another question.
Well, I think for CV, the pseudocapacitance usually takes the form of the peaks are spread, right? Usually pretty far apart. That often is one of the like hallmarks of a pseudocapacitance, or the heights are different. Like there's some of those things, right? Or they're deformed or something like that.
So some people,
I know it's sort of nebulous.
It is kind of nebulous. What I've seen people do, what people are looking at when they're doing any like pseudocapacitive related thing, they're looking at two CVs. And let me get my inking tool out. So they're typically looking at two CVs. And the two CVs are just done under like two different sets of conditions, sort of say.
Scan rates or something.
Well, one is like, and let me see. I can't change the line too much. I'll change it here. And then let's see. Say do it like this or something like that. So they have this kind of like bigger, maybe a bigger CV type of thing. So they have these two CVs. One of them it's kind of like under, I'm trying to say like with the catalyst, without the catalyst, without the pseudocapacitive material. I actually maybe it is a function of, maybe it is partially a function of scan rate. But the idea is whenever you take the difference between these, you'll notice that I have to get that. Oh yeah, it's when you compare as a function. Yeah, so I think you're right, Neil. It is as a function of scan rate. And when you no longer have a square root dependence on the scan rate. So it's
for the peaks, right?
Yeah, or for all of the current.
Okay.
I think it's a combination of like treating this one half. I think this is like X or alpha in the Bruce Dunn method. Where he's looking at the current as a function of the scan rate and using this like X or alpha term, which is in the exponent, and looking at say, hey, if it's, when it's linear, when it's 1, it's purely capacitive. When it's 1/2, it's purely Faradaic. But if it's in between those two things, when it's in between 0.5 and 1, then you end up having the quote pseudo-capacitive behavior. So people will take these kind of different CVs where they'll actually kind of highlight areas where like, hey, when I look at this, when I plot the same things versus the square root or something versus 1, or if I have this alpha or X value, I get like 0.7 or something like that. And that means that
this actually leads perfectly into his next question.
Oh, okay.
As well, because what you're talking about is sort of you could follow up with the next question in terms of EIS. The question is about how the fitting should be, but to just follow up with and hammer home the point you're making precisely, this exponent here of the square root of the scan rate, so to speak.
Yeah.
If you do CV, at different scan rates, and you plot the current or the peak current or the position, right?
Mhm.
Like with the Randall-Sevcik, and you get a relationship that's 0.7. This is almost equivalent in some sense to, for instance, doing impedance, doing a fitting. I'll talk about your question in a second, like how perfect
Yeah.
should it be or whatever. But in essence, it's a similar phenomenon to fitting a circuit to your EIS data and fitting a CPE and getting the alpha value directly. It's a similar, I would interpret that as a similar phenomenon, because if the capacitance is ideal and not pseudocapacitance, right? Alpha would be 1. It's a perfect capacitor. But you likely will get 0.7 or 0.8 or something. And that's a similar correlation where the alpha value of your CPE indicates the degree of non-ideality, which is just another way of saying how pseudocapacitive it is. As far as GCD is concerned, honestly, I'm not super well versed. As best I can tell, for a capacitor with a battery, for instance, um, uh, the shape is different than a capacitor. As best I can kind of tell, with a battery, you usually get charge discharge curves that look, something like this. And so it's there might be sort of changing in slopes, and it's a little bit whatever. With a capacitor, it's more straight. It looks something like this. It's a pretty straight charge discharge curve. And so the effect of pseudocapacitance, as best I can tell, sometimes makes it rough looking, so to speak. And it's similar to what Alex drew with the CVs. It's like a nice looking CV will be, whatever. I'm trying to draw it nicely, it's not perfect, but like pseudocapacitance might have like I shouldn't even draw peaks, actually, because it's more like capacitance is like
it has,
if
it
it's a
has
perfect
both.
capacitor, it'll be flat, let's just say.
Yeah.
Pseudocapacitance might be like, oh, there's a little bump here, right? Or something. Or like
Mhm.
it's, oh, when I do the pseudocapacitance, whatever, it almost looks like there's a peak. It's not, it might wiggle a little or something. It's like, it won't be perfectly flat, almost like anomalous shapes, so to speak, can be indicative of pseudocapacitive behavior. It's unclear to me the extent to which that occurs, other than what Alex talked about in terms of checking for the relationship to scan rate, whether it's square root or 0.7 or whatever.
Mhm.
That is a way to quantify the degree of pseudocapacitance, so to speak, and the circuit fitting. Alpha value is the degree of pseudocapacitance. And then to address your last question here, your first step should be to do Kramer's Kronig on your results, first of all, because you want to find Kramer's Kronig results to your impedance data, because that represents effectively the quote unquote perfect fit. Okay. So number one is, if you do Kramer's Kronig and it doesn't fit that perfectly, you should never expect any impedance, a circuit fitting that you do after, to be better than that. So if you're thinking, well, it doesn't fit like absolutely perfectly, check Kramer's Kronig, because that might be telling you, well, stop trying so hard, because your data are not actually, you shouldn't expect them to be any better than what you're seeing now. I'll show you one. I'll just show you one quick
Yeah,
example.
basically it's this, right? The whole Kramer's Kronig thing is this meme that we said here, which is that you can have like a great, it looks like you have a great fit, but if your Kramer's Kronig is invalid, then it doesn't matter how good your fit is in some ways.
Yes.
Anyway,
so
I just thought oh, wait a minute, we're talking exactly about
good
what
point.
this meme is about.
So for instance, here's some battery data. Actually, it's not capacitance, but it's a similar situation. When I do Kramer's Kronig on this is what I get. It looks like it fits pretty well, but if I zoom in here, you see that it doesn't fit all that. It's generally okay, but it's not fitting perfectly. So in other words, if I did this as a circuit fit and I was telling myself, this doesn't fit perfectly, this is like, it's off a little bit. Well, this is the Kramer's Kronig. I should never expect a better fit than this. This is like testing the validity of the data. Okay. Now, notwithstanding, if you do Kramer's Kronig and it fits really, really well and you're pretty satisfied that your data are valid, you're using something like the error statistics to answer that next question, which is how perfect is it? I would generally use the error statistic with multiple different fits on the same data set. So I pick one equivalent circuit and I get an error statistic of 0.02. Okay. And then I pick a different circuit and I get an error statistic of 0.01. Well, now you have a direct comparison. Well, one of them is lower than the other. So that's a way to say this one's better than that one. Mathematically, that's one way. The other is that I just like to generally try to follow the contours on the Bode plot. Okay. So the Bode plot shows you, like the Nyquist plot's obvious. You want to try to match the number of semicircles, for instance, or something of that nature. Sometimes the capacitive plots are just straight lines, so it's hard to tell. So you want to use the Nyquist plot. Sometimes the phase angle in the Nyquist plot is the one that shows, there'll be one or two dips or something like that. There'll be contours where it's moving a little bit. That's where you're trying to find, in my opinion, where it kind of matches in a lot of cases. Try to get your fit to match that curvature. And part of the reason why that works, I guess, is that the Bode plot phase angle is logarithmic by frequency, but it's not logarithmic by degrees. And so you see curvature a little better. With logarithmic, it kind of, a lot of times it's just straight lines. The curvature is not as, you don't get sometimes as much curvature, so to speak. So seeing how well it matches can get drowned out. But with the Bode plot phase angle, you can see how the phase angle curves and you can see whether your fit matches that curvature. And so I guess that's kind of general advice I would give on fitting.
Mm-hmm. Yeah. No, that's good. That's good. All right. We have a few more minutes left. We'll try to get to as many of the questions as we can. Some we may not be able to get to, or we may actually ask for more clarification. But Azim is asking for water electrolysis. Say if we are using 3 molar potassium hydroxide solution, is it safe to assume liquid medium as a leaky dielectric or conductor? And what is the physical reasoning behind either way? Is it safe to assume liquid medium as a leaky dielectric or conductor? I don't know what he means by.
I'm not sure what leaky dielectric is.
Yeah.
I don't know what that means.
It's a 3 molar potassium hydroxide is it's not like a pure conductor, but it makes it makes water more conductive. Do you know what it says? What leaky dielectric?
Taylor-Melcher leaky dielectric model. The quick AI overview, which I don't like because it's not always right, but it says a material with a very low but non-zero electrical conductivity, behaving as a dielectric, basically as an insulator, but with some degree of electrical leakage. I don't know that would describe KOH. It's pretty electrically conductive.
Yeah.
It's so low conductivity. This looks like it's something leaky dielectric. As best I can tell, it looks like the concept of a leaky dielectric is something that has low electrical conductivity, but can be almost induced into acting as one in some manner of speaking. And so I don't know how you would use that phrase with KOH. 3 molar KOH is quite conductive.
Yeah.
So perhaps it's possible that I don't understand the question. We don't understand the concept quite well. But it's not a conductor as well. It's not a metal.
Yeah, it's not like a pure. It's not a pure metal.
No, it's not a metal. It's a conductor of. It's an ionic conductor. It's not an electrical conductor.
Yeah.
Right. So the electrolyte in an electrochemical reaction conducts charge via ions, anions and cations, not conductor as in conducting electricity. Electrons do not just flow freely through solution. That's not what happens. You need a tremendous amount of voltage to make an electron just shoot right through solution. In fact, if they did, electrochemistry as a science would not exist.
Yeah, it'd be very different.
If electrons could just flow right through solution, you wouldn't even have a battery. It wouldn't exist. That's why they flow through the external circuit, which runs your phone and allows you to surf Instagram for 5 hours. So if they went right through solution, you wouldn't have any Instagram. So I'm very sorry. Ultra pure water, maybe. Yeah, that makes sense.
Okay.
That's what I'm thinking, right? It's like something that's very, very insulating, basically, but perhaps can have some minor conductive properties and behave in that way in some conditions, I guess. If you put a field through it or something, I guess. I don't know. I think we'll have to leave it for there though, because I'm not sure we have any more expertise on that topic. So,
yeah.
It's Taki. I don't know what SCs is.
Yeah.
What's a better choice for SCs? Graphene oxide or reduced graphene oxide? First of all, I'm not sure. I don't know what is SC. I'm trying to think. For semiconductors. Semiconductors, or I don't know what this means. And honestly, I don't know if I would know the answer. Even in spite of that, whether GO or reduced GO is better. We're gonna have to leave that. I'm sorry. I don't know that I have any expertise about that.
Yeah, no, me neither.
At all. So I'm very sorry. Elijah, I can show this as perhaps the last thing if you'd like. I have data to show this.
Yeah, or you can tell them this is for the RRDE webinar, right?
Yeah, that is the main thing. I can show you a Tafel plot really quickly. So Alex, maybe you mean me. Anyway, one of us talked about kinetic current to calculate the Tafel plot. I was wondering if you could do a walkthrough of the sample Tafel plot and slope. I can kind of show you very briefly. My more thorough answer is that I've done a 2-part RRDE Levitch, Katecki-Levitch, Tafel analysis webinar. It's on our YouTube channel. It's in the webinars playlist. I've done it 2 or 3 times. And the second part 2 of that webinar series, I quite literally do an entire Levitch, Katecki-Levitch, and Tafel analysis live to show folks how to do that. And so this is where this data comes from. But what I have here, are some data from that webinar. I'll run through this in 1 or 2 minutes. This is a sheet that I use in this webinar. You can see all the equations. This is the Levitch equation. This is the diffusion coefficient from that. This is the Katecki-Levitch equation. This is how do you get the diffusion coefficient. This is kinetic current and heterogeneous rate constant. And this is the Tafel equation. All the stuff here on the left. These are all the things, right? This is data that I collected doing RRDE at these rotation rates. So I know it's a lot to look at. I'm just sort of trying to step you through it very briefly here. The point is I did all the analysis of these data at different rotation rates. I got the current and I used the Katecki-Levitch equation, which is this one, to obtain values for the kinetic current here at each potential. And those data are shown here. So this is each potential, the current at each rotation rate, and then done Katecki-Levitch analysis, you get the kinetic current at each rotation rate. You then take the log of that kinetic current, and that's how you get the Tafel plot. And so what I have here is log of the kinetic current and potential. You see I have these columns copied. And so what I'll do now is go to our software. It's an easier way to do this actually than in Excel. And so in Aftermath here, let me make a new plot. And so I'm going to just ignore the units just to be quick here. But the units are on the y-axis. I have the overpotential. On the x-axis, I have the log of the kinetic current. And so this is a Tafel plot. So again, this is overpotential on the y-axis, log of k on the x-axis. And the 0 here is 0 overpotential. So this is like on the y-axis here, this is where I have no driving force. And so as I drop down, as I go down, 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 I'm driving the reaction more and more. And eventually you see the slope changes, as Alex was talking about before. This is like I'm getting too big of an overpotential. Maybe I've got something else happening. I've got other reactions happening. So when I'm getting my Tafel slope, I would focus usually on a region that's relatively flat if I can. And so I would, there's up for interpretation here, like where exactly would I get the slope? This is one option. This is a slope of about 60. So this would this would suggest, for instance, like, oh, 2 electrons transferred. There's definitely some possibilities here that this, maybe this, you might choose, for example, well, I need 200 millivolts of overpotential, down in this region here, like 160, 200. I should do my slope where I have an overpotential of at least 150 millivolts, because that's where it's really irreversible. And now I get a slope of 120. That's 1 electron transferred. So that's a better slope place. The reason I'm being vague about this is because these are data that I have for a webinar. It's not meant to be publication worthy analysis. I like to use these data to talk through strategies, for example, and then you with your data will apply perhaps what's most appropriate. But this is a way to do that kind of analysis, to sort of pick your baseline, pick the overpotentials that make the most sense. Sometimes you sort of do it the way I'm showing you, which is that you find where the slope makes the most sense. For instance, like this is 120. Okay, well, that means that this set of overpotentials is the appropriate set of overpotentials that I should be analyzing. You sort of do the opposite. You would ideally say, I want to do the slope at these potentials because that corresponds to whatever. But in this case, it's like, well, I know at these overpotentials, the slope is whatever. So that means these are the correct overpotentials. You're sort of doing both things at the same time. You're figuring out what the right overpotentials are and what the right slope is. And sometimes that's done visually and experimentally. So again, the webinars that I did previously, I do a lot more of that in depth. So I would encourage you to join as a tier 2 member. You can watch those webinars as well.
It's 3:00 right now. This is usually Eastern Standard Time. This is usually when we've been live streaming for 2 hours now. So we see that there are still a bunch of questions. We apologize. We will be doing this next week Friday. We'll put up a thing. So please join us then. Ask the questions if you can do it earlier. If the earlier you get us the questions, the more likely it is that we'll be able to answer them.
Yeah.
So with that said, thank you for coming, and we'll see you next week.
Yeah. Everybody have a good week, and we'll see you next time.